So Shreyas, this was it, right? P orbitals, right? This is what we were doing, right?
Yeah.
Okay. So he has 1s orbital, 2s orbital, 3s orbitals, right? And then we have p orbitals, right?
Okay.
Okay. So let's spin quantum number has no classical analog, and this is the thing. This gives you a hint of spin quantum number because we are able to split. Okay.
Okay.
Okay. We are able to split a beam of atoms using a magnetic field. Okay. Now we start with atomic orbitals, right? So yeah, we started with atomic orbitals, and before that we were here, right? So where is the no problem? So I'll just add a page here. So first we'll go to the quantum numbers. Huh? Okay, we'll revisit them. So we have n, right? Is the principal quantum number, right? Yes, no.
Sorry, sir, I was on mute. Yeah. Yes, sir.
Okay. And then we have L,
Yeah.
azimuthal quantum number. ML, magnetic quantum number. And I have MS, spin quantum number. It has only two values possible, plus half and okay.
Hmm.
And now we start. So n can have integer values, right?
Yeah.
So n equal to 1, 2, 3, 4, and so on. L values will go from 0, 1, 2, so on till
Yeah. Till
n
M.
minus 1. ML values goes from minus L, 0 to plus L, right?
Yeah.
Okay, this is how we were doing. And we also said that L value gives us a specific information.
Hmm.
And what is that? L and orbital, right?
Right.
So if I have L as 0, orbital is
Yeah. S,
1,
P,
2,
D, and F. Yeah.
F, G. Now the number has started after F, the normal numbering. Huh? Got it?
Yeah.
So we discussed all this, right?
Yes.
Okay, you remember this, right? I am
Yeah.
just yeah, I think this we have discussed. Anyways, I think it was Vivier and RC. Okay, no problem. Yeah, we were somewhere here. We were here. I just want to see where. Yes. Okay. Yes. So this is what we did, right?
Yes.
And okay, now it's fine. Now you see, then we said that the number of values of ML. Okay. The number of values of ML tells us how many orbitals, right?
Yeah. Yes.
How many? You can say, yeah, no problem. How many orbitals are there? Okay. So now we again turn back to this. So I have one. Okay, let's. I really wish home insert. Why do I have to always do some magic thing with this in order to get? One second. So they need to work so hard on this product. It's like every time I have to pull up some magic in order to.
Mm.
Okay. See the stupidity, right?
Yeah.
I have to insert a table. Now the table has disappeared. Why it is like this? Only God knows. Huh? Right. Okay. Great. And now I have to pull some more magic, I think, too. Oh, yes. There it is. Go to this table and insert columns right and L. Insert column right. Okay. And insert rows below. I think this should do, but yeah, okay. And then I have to expand this table because it went. Anyways, see, I'm just tired of this, so I'll just shift to this. And L
Yeah.
ML because I don't know what I have to do to put the subscript, but yeah. No, I don't want to do that. How can I just expand this table so that it becomes bigger? Okay. Oh, please. I think no, 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 no. All text I don't want. Let's yeah. Okay. Anyway, still nothing has happened, huh?
Yeah.
Stupid. Okay, no problem. So L will be 0, ML will be 0,
Mm.
and I think let's say I instead of MS because we will just say that which orbital is this. Okay.
So, like the value of the spin quantum number will be given, right?
Yeah, yeah, don't worry about that just now. Orbital is 1s. Okay.
Yeah.
N is 2.
Yeah.
So
And L is
L
1.
can be 0. It can also be 1, right?
Yeah. 0.
So This will be 0. Here it will be -1,
0
0,
plus 1.
and we'll have +1, right?
Yeah.
So here only I have this 2s orbital, but here I'll have 3 p orbitals. We'll call them 2px.
Okay.
And by any chance, have Microsoft given us an option for a subscript here? I don't think so. Great. Why will they give? What is the need? Yeah, there's no need for a subscript here. Stupid. 2py, 2pz. 3. Okay?
Okay. So 3 orbitals.
Yes. Okay.
Sir, but then why 2p?
That we generally say as a complete subshell, so we just say 2p. Okay? It's like we say India, then we start making the states, huh? Karnataka, Andhra. Huh? So
Okay.
2p is the India and 2px is Karnataka, 2py Andhra. Got it?
Okay.
So this is giving us this, right? So I'll put n 2 here also, right? So that then it comes 3, it will be 0. So this will be 0. We'll call this 3s, right?
Yeah. Mm.
Okay, now I think we can go to the table and insert this below, insert, insert, insert.
Sir, wouldn't it just be more convenient to draw it?
No, no, no. Of course, it will be convenient, but it'll be. I thought it will be cleaner. Now I'm stuck with it. Okay. So, anyways, 3, 1 again, right?
Yeah. -1 0 plus.
Let's give me some advantage here, Microsoft. Yes. Huh? So, so see, we are going to get. Come on. This is like everything. It's like more. See, I cannot put a cursor in between. See, this is so.
Sir, uh, hold the space bar
Okay.
so you can go to whichever place you want.
Oh my God. Thanks. See, I'm learning from you. 3. But why is not this is here? Why cannot I tap it here?
Yes, sir.
What is the use? Where to do this like this? Although it's not bad, but right? I
Yeah.
should be able to tap it, right?
Yeah.
But anyways, thanks. So now for 2, I have -2,
-1
-1,
0 1.
0, and +1, and +2. Okay. So, okay, now I have to write them. So 3D XY,
Yeah.
3D YZ, 3D ZX, 3D Z square. Great. Yeah, I will never make a table now. 3D X square minus Y square. Because it's like, no, no way. Anyways, even Google is much better than this. Learn this, learn. So yeah, over, I think we would have done much better if we would have stuck to our My God, and you just cannot do anything with this table also.
Hmm.
Any idea how to increase this? Just this length.
Yeah. So just tap on the whole table. Can you like expand it, or does it just move?
Let's see. Now what? Now you want me to expand it from here?
So does it expand?
No, it does not. The only thing which is expanding is their paycheck.
Hmm.
See, this is supposed to be so easy and intuitive, right? You just put it and pull it, right?
Yeah.
Anyways, so this is the last time we have drawn this. And anyways, so this is giving us the number of orbitals. I'll come back here. So see, then we talked about the nodes. I want to talk about the nodal surfaces actually. Okay. So I'll just now come back to this. After having such a great adventure with this. Nodes. This is a very important concept. Okay.
Hmm.
And it goes like total nodes. Node is the area where the probability of finding an electron is zero, right?
Okay.
Nodes, no, and no. So electron will not be there. So total nodes is n minus 1. Then we have angular nodes.
So nodes are the places where you can't find electrons.
Yes, the probability of finding the electron is 0. Angular nodes is L, and whatever remaining are radial nodes. Huh?
Okay.
Got it?
Okay.
Okay, now we'll do some. So let us consider 1s orbital first. So total nodes,
Uh, n minus 1 is 0.
2s.
Only 1.
And angular node,
Uh, 0.
we could have made a table here. But now I'm so scared.
Hmm. Yes, so 0.
Yeah, but I think we should not be scared. Let's try a table again. And how do we make a table? Oh, yes. I put this here. Then they give me the table option. And then, okay, orbital, total, angular, and radial. 4 we need, right? Insert. First, we do this, insert, right? So, yeah, and then below and quite below. I think this table will still make sense because
Yeah, no.
yes. And from here, I think yeah, let's at least get 36. Huh? Okay. So orbital. Okay. Let's have some colors here. How bad you can be. Orbital. Total. Oh, great. Every time I have to. I hope that. Okay. Yes. And select on table and Great.
Hmm.
Orbital total, right?
Yeah.
Total
Uh,
nodes. Then I have angular nodes.
hmm.
Angular nodes. Great. Now I think it will expand like this. And radial nodes. Great. Great is radial nodes. Okay. Total nodes is n minus 1. I want it small. Thank you. Oh my God. I've switched on the autocorrect, but still it is there. This is L, and radial nodes is given by n minus 1 minus L. You can also write n minus L minus. So now we start with 1s. So this is 0, 2s. This is 1. This is 0, right? So in s orbitals, because they are spherically symmetrical, we will only have uh, radial nodes. We never have any angular nodes because L value will always be 0 for any s orbital, right? Yes. Right? Hello?
Oh, sorry, sir. I was on mute. Didn't realize.
Okay.
I keep on touching the keyboard.
No problem, no problem. So s orbitals will always have this, right?
Yeah.
Then I have 2p, total node is 1, angular node is 1, radial node is 0. Then we do for 3s, total nodes 2. So
Yeah.
s orbital will always have 0 angular nodes, right? All of them will be radial nodes.
Okay.
And 3p,
3p. Yeah.
total nodes 2,
2. Then
angular node will be 1 and 1 radial node, right?
1.
3d, total
Uh,
2,
2.
angular nodes 2, radial nodes 0.
0.
Okay, table, insert, rows below. Okay. So S begin from 1, P begin from 2, D begin from 3, F will begin from 4. Okay.
Yes.
So let us have 4S, 4P, 4D.
Sir,
Okay.
I think if you just hit enter, you'll automatically create a new
Okay, hopefully. No.
word.
Insert. Okay. No problem, no problem. It's okay. Now I made my peace with it. So total 3 nodes,
Yeah.
angular node 0, all of them will be radial nodes, right?
Yes.
4p also 3, but we'll have 1 angular nodes,
Yeah. So 2.
2 radial nodes.
Yeah. 3, 2, 1.
4f, 1 sec. Oh, okay, my Amazon package has come. But anyways, so again, this is 3, this is
2.
2, this is 1, right?
Yeah.
And 4f,
E.
I'll just count. Okay. Okay, so I had ordered some bookmarks actually. 4D and 4F, 3,
3, 0.
0. Got it now?
Yes.
Okay. But this table is very tiring thing in this. Anyways, and how do p orbitals look? See? Okay. So p orbitals look something like this. See? Dumbbell shaped, huh? Okay.
Okay.
Note that if we are drawing 2px, this dumbbell is along the x-axis,
X-axis, Y-axis, Z-axis.
and this is on along the y-axis, and this is along the z, right?
Yeah.
Okay. This also. D orbitals. So this is anyways. So p orbital, we talked about it having a nodal plane, right?
Yeah.
So angular node, right? So see, this plane is the angular node. This is where the probability of finding it is 0, where we have to cut it in between. So see, it is more like a phase, or you can see it like a color change. You can also like, whenever there is going to be a color change along that plane, it will be 0. It's like you can assign arbit sign like minus and plus.
Okay.
So whenever you have to go from minus to plus, you have to go through 0, right?
Yeah.
So that is the node. Okay.
Okay.
Okay. And see, these are the d orbitals. See. Okay.
Okay.
So what happens is these dxy, dyz, dzx, they are at 45 degree to the axis. If we are drawing dxy, for example, then they will be in the xy plane and they will be at 45 degrees. Got it?
Yeah. Okay.
Okay. They are at the 45 degrees. Okay. Right?
Yeah.
dxz again, see 45 degree, 45 degree. The only one along the axis are the one which are squared. Okay. So dx square y square will be along the x and y lobe axis. Okay.
Okay. And then
Okay. Dx square y square means the lobes are along the axis. Dz square means the lobe is along the z. And also you can see there is a ring sort of there, right?
yeah.
Fancy, huh? So this is the Lord of the Ring orbital.
Mm.
Okay. So this is it.
Okay.
And see, now there, see 4D, for 4D orbit, for a D orbital, right? We said that there will be two angular nodes, huh?
Oh, yeah.
You see that these two planes, huh?
Right.
We're just splitting these. You can imagine this is a fruit and you are splitting it in half. So,
Yeah.
okay. DZ square is more fancy. It's like conical nodes, huh?
Mm.
Got it?
Okay.
Right? So these are the angular nodes. We'll come to these more. Uh, but yeah, for the meantime, this is how it is. Okay?
Yeah.
Okay.
Yes, sir.
Right. Okay. So I think this is more. Now, do this. Uh, this example actually. So this is also an example. We talked about this, the energies of the levels,
Hmm.
right?
Right.
So we said that in the hydrogen atom, what is going to happen? In the hydrogen atom, the energies will depend only on, right?
Hmm.
Only on what?
Yeah, only on the
N,
n. Yeah,
right?
right.
Only on the
Correct.
N value
Because
they
it
are
doesn't.
depending, right?
Yeah, because it doesn't have any fancy orbitals. So,
No, it is not due to that. It is due to that when we apply that wave function thing, then we get only dependency on N. But yeah, so
okay.
it depends only on the N value. Okay.
Okay.
Okay. So that is the one thing which we must know. So it means that, see, 2s, 2px, 2py, 2pz orbitals, they are all on the same level, right?
Right. Yeah.
Right? They should have y, x, and they should have named it z, but anyways.
Hmm. So how do you get the 3D z square, 3D x square minus?
Oh, that is beyond your scope for a moment, but I'll show you and don't worry. You have heard about complex numbers a bit?
Yeah.
Yeah, right. So there is something called linear combination. Okay. So we do linear combination of complex number. These wave functions, they are complex wave functions. Okay, they are like not the simple things, but we'll come to this.
Hmm. Okay.
So for the meantime, we are just good
Hmm.
enough with this that
Right. Familiarizing me with the.
yeah. Okay.
Yeah.
So that is it. 2px, 2py, 2pz, 3pxyz. So so anywhere where we have 3x, so
Hmm.
that was the game, right?
Okay.
Okay. But in the case of multi-electron atoms, where we have,
Hmm. Yeah. Other than hydrogen.
yeah, then we have the energy levels will depend upon the n plus L values. Huh? Okay. Here,
Okay.
n plus L value. So higher n plus L value means higher energy. See, convince yourself.
Hmm. Yeah. So more orbitals. Um,
Just see how you will distinguish which is higher in energy.
yeah. An increasing number of orbitals gives higher energy. Hmm.
Right?
Yeah.
So if I give you two orbitals, you can tell me which is higher in energy?
Uh, okay, sir.
No, not okay. You just check and see how you will calculate, how you will figure it out.
Yeah, and it depends on which shell also.
No. First, simply we will calculate n plus L.
Okay. Sir, for which one?
Suppose we are given 3s and 2p. Okay. So
Hmm.
how we will go about?
I think 3s has more energy. No. Oh, wait.
So first we'll calculate the n plus L value.
Hmm.
Okay.
Yeah.
Higher n plus L value means
Yeah.
higher energy. Got it?
Yeah.
Right?
Yeah.
So
So
in
that,
this particular case, what we have? We have a tie, right?
yeah, both of them have equal 10 plus L values.
So n will decide. Got it?
Yeah.
In case of a tie. Got it?
Okay.
Okay. So 2s and 2p, how we will decide? 2s has n plus L value of 2, right?
Yeah, and 3 plus. Yeah,
And
3.
2p has 3, right?
Yeah.
Got it?
Yes.
So higher n plus L, it implies higher energy.
Mm.
In case of a tie, what happens?
The one with the higher atomic, I mean the higher
N decides.
n value. Yeah.
Higher n plus higher energy. Got it?
Yes.
Okay. So this is how we'll go about this. Okay. So we have to write down the electronic configurations. Okay. That is the first thing. And this is the order of the energy. This you'll see. Okay.
Mm.
They'll draw like this. In a lot of books, you'll see like this. Okay. But we will not do like this. Okay. So we have a mnemonic. We'll start like this. Okay. School, public school, public school, Delhi public school, Delhi public school. Got it?
Okay.
So two public school and then Delhi public school. Now I'll again write it school. So repeat after me, yeah, once.
School. Yeah.
Okay. You repeat, I'll write.
School. Public school. Uh, public school. Delhi public school.
Okay. Now we will number this. For S, we start with 1, right?
Hmm.
1, 2, 3, 4, and 5, right?
Yeah. And then,
For
okay.
P, we start with 2, right?
Yeah. So then 2p, 3p, 4p.
For D, we start with 3, right?
Okay.
Got it?
Yeah.
Now, in any any orbital, we can have two electrons. So S has only one S orbital, so two electrons, 2p subshell has right
Hmm.
three orbitals. So in the p total 6 electrons can be accommodated, but in any p orbital we can give only 2 electrons. Okay.
How much? I mean, how many electrons can be accommodated in
In any orbital only two.
okay.
Okay. We'll come to this. Okay.
Uh,
So okay. So in any orbital only two, but there are three 2p orbitals, so p subshell will have 6, right?
yeah, because okay.
2, 6, 2, and D can up to 10, right?
Hmm.
P6 and this 2. So if we add the 2, 4, 6, 10, 12, 18, 20, 30, 36, 30. So you can write electronic configuration till 38 atomic number, right?
Yeah.
Let us go back school, public school, Delhi public school, and Delhi public school.
Hmm.
So we can repeat this Delhi public school also twice.
So does it all repeat twice only? Or
Not really, with an F orbital will also come, right?
No, so
So
2
it
L.
will be like school, school, public, school, public, school, Delhi public school, Delhi public school. F orbital comes,
Yeah,
Delhi public school.
and that continues twice, and then
As this is sufficient, I think, for the meantime. Let's count how many we can fill with this. 2, 4, 6, 10, 12, 18, 20, 30, 36, 38, 48,
mm,
54,
54,
56,
6.
14, ooh, 70, 80, 86, 88. I think this is enough, huh?
Yeah.
Yeah. Or then again we write this. School, school,
Mm.
public school,
Delhi public schools.
public school, Delhi public school, twice, right?
Yeah,
F Delhi public school.
yeah. And then it goes on.
Okay, and after that, what it was again?
F F Delhi public schools. Then G F DPS.
I think so. So I think maybe this is the one. So yeah, now we can 2, 4, 6, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56. Are we counting correctly?
Mm. So 10, 12, 8,
These,
20,
these, 36, 38.
38, 48.
Yeah,
Yeah.
this is 70, right?
56.
Plus
Then
16, 72, huh?
yeah.
82, 88, 90, 104,
Mm.
124. I don't think so. There are that many elements also.
Yeah.
There are, I think, 6. So yeah, see, right?
Yeah.
You can write the electronic configuration of so many things. Okay, now we'll come back to this. See, now how do we write the electronic configuration? Okay, there are certain rules, okay?
So this is the location of, I mean, the prob
Electrons, right?
yeah, the probable position of everyone.
Yes, 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 yes. We'll come that to. You see, now since we have defined an orbital as a region, okay, we cannot pinpoint.
Yeah.
Okay, so an orbital is a simply a region where the probability of finding that electron is maximum, right?
Yeah.
Got it?
Okay.
Right?
Hmm.
Right?
Yes. Yes.
So now we are going to come to certain rules. Okay. The first is Pauli's exclusion principle. Okay.
Okay.
So let's go back a little. Yeah. See. So we have something which we call Pauli's exclusion principle. Okay. So Pauli's exclusion principle says that no two electrons in an atom can have the same set of four quantum numbers. Okay.
Okay.
So basically what it is saying is that whenever this is the Pauli's exclusion principle. Oh my God. It is not the light one, right? That's what I thought. No two electrons in an atom can have the same set of four quantum numbers. Okay. So what they are saying is essentially, for example, when we are trying to fill in hydrogen, we'll fill it like this, 1s, and we'll this means that plus half spin. Okay, upward. Got it?
Okay.
So now all the quantum numbers are defined. N is known, N is 1, L is equal to 0, ML is also 0, and spin quantum number here is plus half. Got it?
Yeah. Okay.
Now, when we come to helium, right, we can either write like this or like this or write like this. So Pauli's exclusion principle says that we cannot do this because in these cases all the four quantum number will be same. So in essentially what he's saying is that whenever you try to put the second electron in the orbital, it must be having opposite spin. Got it?
All right.
Okay.
Yeah.
Because
So,
in an orbital, NL, ML values will be the same, right?
hmm.
So the only way we can differentiate is by the MS value. Okay.
So this 1s square and 1s.
2, 1 is 2.
So what does the 2 show?
2 means 2 electrons, huh?
So 2 electrons in
So
one.
it means in the 1s orbital there are 2 electrons. Here it is saying in the 1s orbital there is 1 electron. Got it?
Okay.
Here 2 electrons. Got it?
Okay.
So this is the electronic configuration. Till now you just write for helium 2, right?
Yeah.
So
Okay.
where is this 2? It is in 1s orbital. Got it?
Okay.
And it is having opposite spins. Okay?
Uh,
Got it?
okay.
It cannot have this parallel spins. Okay?
Hmm.
So this is what is Pauli's rule. Okay.
So the up and down arrow shows the spin.
Plus half and minus half. Huh?
Okay, for those 2 electrons.
Yes, right?
Okay.
Okay. So this is what they are saying, that parallel and anti-parallel spins of two electrons plus half and minus half, but we know that
Hmm.
so this is for you.
Yeah.
So what they are saying is, so we know that spin quantum number does not have any classical analog, right?
Yeah.
Okay, if you remember. See, Pauli's exclusion principle is something which we define something as paramagnetic substances. They have net unpaired electrons, okay, and they are attracted by magnet. And diamagnetic substances do not contain net unpaired spins and slightly repelled by a magnet. Okay,
Okay.
so helium is diamagnetic, right? Hydrogen is paramagnetic, right?
Right.
Great. So yeah.
Uh, hmm.
Lithium again paramagnetic, right?
Yeah. Okay.
See, lithium will write like this, huh?
Okay.
3 electron, SS, right?
Hmm.
School, huh? Now, this is a shielding effect. We'll just come to this later. Okay. So what they are saying is that experimentally we find that 2s orbital lies at lower energy than the 2p orbital. Why? That is because 2s and 2p orbital, first of all, they are larger than 1s orbital, obviously, right? Because we
Right.
are in the 2, right? Principal quantum number is 2, right?
Right.
So an electron which is in these orbitals will spend more time away from the nucleus than an electron in the 1s orbital, right? 1s orbital will be closer to the nucleus, right?
Correct.
So we
So
can say that we can speak of 2s or 2p electron being partially shielded by the attractive forces of the nucleus because they are far, so attraction will be less, right?
yeah.
Right. So it reduces the electrostatic attraction. So this important is that it reduces the electrostatic attraction between the protons in the nucleus and the electron in the 2s or 2p orbital. So obviously further they will reduce the
Hmm.
force. So here the 1s electrons effectively shield both the 2s and 2p electrons from the nucleus, and the 2s orbital is more penetrating than 2p orbital. We'll just come to this again later on. But
Oh,
anyways, for the meantime, we'll just continue with the uh, see beryllium is same 1s2 2s2. We are just going into the electronic configurations. Okay,
hmm.
see boron, right? 5.
Yeah.
Okay, now you see when we are stuck in when we are in boron, after that see what happens. Now after boron comes carbon. Now what we can do is we can do all these arrangements,
Hmm.
right?
Okay.
So which one we will do? Okay. So another rules comes Hund's rule of maximum multiplicity. Okay. It says that first the most stable arrangement will be where we will have greater number of parallel spins. Okay.
Hmm.
Okay.
The most stable arrangement.
Okay. So here we can see that one is parallel, one is anti-parallel.
Hmm.
Same is here. So we'll go here. Okay.
Okay.
Got it?
Uh.
Both are parallel in the last one, right?
Hmm.
Okay.
Sir, so how does uh, okay.
Got it? See, I have to fill 2 electrons.
Okay. Then
So these are the possibilities.
hmm.
Okay. So I'll fill it like this. So in A and B, they are cancelling each other. Okay.
Okay. So so C is not very stable.
C is the most stable. C is how it is. Right?
Okay.
Okay. The most stable arrangement of electrons in subshell is one with the greatest number of parallel spins. Okay. So this has the
Okay.
greatest number of parallel spins. There are 2 parallel spins here, right?
Hmm.
Right?
Yeah. So okay.
Okay. So the for carbon, we'll write it like this. Got it?
Hmm. Yes, sir. Sir, so how do you determine which one has a parallel spin?
Both are pointing upwards.
No, sir, like if you want to count it.
Both are here. In the first one is up, one is down, right?
Yeah.
So in the second one again, one is up, one is down, right?
Hmm.
So in the first one, there is no parallel spin, right?
Yeah, there's no parallel spin.
In the second also there is no parallel spin. In the third there is parallel spin, right?
Yes.
Okay,
Okay.
that is the meaning of the parallel spin. So while we are filling, we fill it like this, huh?
Hmm.
Okay.
Okay.
See, let's go back to this.
So the last,
Here we can understand if they are in the same orbital, they will have larger repulsion, right?
yeah,
So A will have least energy, maximum energy, maximum repulsion. So it has to be amongst B or C, right?
right. But
Okay.
because B doesn't have the
Yeah.
parallel
But
spin.
now see, the choice of C over B is more subtle, but can be justified on the theoretical ground. The necessity for electrons with parallel spin to occupy different degenerate orbital is due to spin correlation, a quantum mechanical effect that makes electrons with parallel spins have a tendency to be far apart from one another.
Okay.
Okay, so they want to be far apart. Now, so this is how it has two unpaired carbon has two unpaired electrons, right?
Hmm.
Now, other thing is now we go to nitrogen. See,
Uh,
nitrogen. See,
hmm. Okay.
okay, and then we have oxygen. Okay, and now one second. General rules they are saying so. They have recapped the general rules. Okay, we'll come to this. Come to this. Yeah, let's just come back to this. Okay. Oh, yeah. So, yeah, Hund's rule, and let's put it here. Hund's rule. Okay, let me put in apostrophe.
Okay.
And I'll add a page here. See. Now, how we are adding, huh? For multi electrons. So, I know first of all that the orbitals are like this, huh? Oh, we have 1s orbital. Then at higher energy, I have 2s orbital, right?
Yeah. And
Then
then
I have 2px, 2py, 2pz, right?
hmm.
Okay. So first we'll do for hydrogen. I'll keep on,
Hmm.
drawing. So first electron will come. This is done, right?
Hmm.
Okay. Then we come for helium. Second electron come, but Pauli said it must come with opposite spin, right?
Right. Okay.
Okay. Then let's draw it here again. 1s, 2s, 2px, 2py, 2pz. Okay. Same thing.
Hmm.
Three electrons, 1, 2, and now it will go to this one, right?
Yeah. Okay.
Beryllium,
Same thing for one. Uh, up, down, up,
right?
right. And
Boron, right?
right.
Carbon. Let's use some colors. this, 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 and this, right? Okay.
Okay.
So pairing, there's an alternate way of saying Hund's rule that pairing does not start until each degenerate orbital has one single electron each. Huh?
Sir, what's a degenerate orbital?
Degenerate orbital means orbitals which are equal in energy.
Hmm.
Okay.
Okay.
Got it?
Okay. Uh,
Now you think of nitrogen.
and then there's one more standing line. I mean, there's one more upward arrow.
Yes.
The third. And then
Okay.
oxygen, there's one downward arrow on a 2px. Uh, yeah.
Yeah.
Uh, neon, fluorine, there is one downward arrow on.
So initially when we are doing it, they will have each orbital will have single electron with spin up. Okay. Parallel spin. Okay.
Okay.
Before pairing up. So carbon is like this. Now we go to, let's go to nitrogen. 1s, 2s, 2px. And this is only for degenerate orbitals. Okay, 2px, 2py, 2pz are all degenerate, even in multi-electron, because n plus l is same and n is also same, right?
Yeah. Okay.
7, right?
Hmm. Then oxygen. Yeah.
8. So first each will get one. Okay,
Okay.
now pairing starts. Got it?
Yes. So then after that, the degenerate orbitals keep on shifting uh, to higher and higher, uh, like 3D and all that.
Yeah, when once these are filled, we'll go to the
Hmm.
4s, right? 2p,
Yeah.
3s. Huh?
Hmm.
Got it?
Okay.
Okay.
Hmm.
That order we know by school, public school. Huh?
Yeah. Yeah.
Okay. Fluorine. Seven. Got it?
Yes.
And finally we have it's first we'll do like this. Then we'll do like this. Okay? Got it?
Yes.
So these are the rules. Okay. Read these. They're very important.
No two atoms. Yeah. Okay, sir.
Okay.
Hmm.
Now this is Aufbau principle. This is called Aufbau. It's not Aufbau is a German word which means building up.
Okay.
So it says that Aufbau principle that as protons are added one by one to the nucleus to build up the nucleus elements, electrons are similarly added to the atomic orbitals. So German word Aufbau means building up.
Okay.
It is just like how we write the electronic configuration. Okay.
Okay.
There are two irregularities. These are very important. Okay. First is chromium. Its electronic configuration is 4s1 3d5 and not 4s2 3d4 as we might expect. And similar break-off patterns for copper, chromium and copper. Here the 3d10 4s1 we are expecting instead of this. This is because there's a greater stability with half-filled 3d5 and completely filled 3d10 subshells. Okay, so that is why this switching occurs. So normally we will expect that chromium will be 4s2 3d4. Okay, normally we are expecting chromium to be 4s2 3d4. Okay,
Okay.
so but what is happening is
Sir, so how do we get this 4s2 3d4?
it's the same SSP as DPS. Chromium is 24, right?
Yes, sir.
Okay. So 24, 2, right?
Hmm.
Right?
Oh, okay, so where it becomes 24.
Okay. Got it?
Got
Atomic number is 24 of chromium. Huh?
it.
That periodic table is not just for hanging there. Okay.
Yeah.
So 4 is 2, 3d4. So instead, what happens is they switch and this become 4s1 half filled and this become also half filled. So half filled 3d5 they are more stable. So that is why this switching occurs for chromium. Very important. Huh?
Okay.
Okay. Similarly, for copper, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9, I think. Let's count. 29, right? Copper is 29. Okay. Yeah. Z equal to 29. This is Z is equal to 24. और ये क्या है? Z equal to 29. Got it?
Okay. Sir, but then
So here also what happens is this switches.
sir 3d9, how did 9 come?
Total 29, na?
Yeah. Okay.
So in D we can have maximum 10, right? We have 5 d
Oh, right.
orbitals, right?
Oh, right. Yeah. I forgot.
Okay. For S1 3d10, a switch takes place. Okay.
Yeah.
These are important, huh? Okay. Got it?
Yes.
Clear? Here are the electronic configuration. We can write it. You can check. Okay.
Mm.
These are quantum dots. We are not supposed to. I mean, we can look at them. They are
Yes.
just,
It's,
yeah. I told you to read them, right?
yeah.
They are like the wave particles of the, right? Electrons. Electrons are confined to a very, very small region. This is what starts happening, and now they have started exploring these, and they can see this chromium copper. Let us add a bit lighter shade of. Uh,
Yes, sir, the excess DPS, FDPS thing is very useful.
yes, yes,
So with that huge diagram with the arrows and all, yeah.
yes, yes. Oh no, I think we'll stick with the green. So chromium is important and copper is important. This is exams they are asking continuously. Got it?
Mm.
We can write all the electronic configurations. Huh? Okay. Yeah, where was that public school thing? Here.
Mm.
Nice.
Mm.
And this is the summary. And these are some problems which we did, right?
Yeah.
I think we did majority of the problems. Let's see. Practice exercises. I think yeah, these level 1 problems. Okay. And as you scroll down, you'll see this level 2 problems. Okay. Hello.
Yes, sir. Sorry, I was on mute again.
Okay. No problem. No problem. See, now I don't want this. I just want it to be. I want to. How I will bold it now. Okay. Thank God.
Okay.
So this is level 1. Okay. This has not made any change here. Only here. So I'll just leave it like that. The level 2. Then you see level 3.
Okay.
Then there's more than one option correct. So match the columns. Let's start here. Okay.
Yeah.
Then we have some assertion reason. Okay. Some subjective problems and like this. Okay.
Mm.
And these are the answers. Huh?
Yeah.
Okay. Please attempt and then see. Anyways, so I want to go for to or yeah, let's leave and let's done this. Yeah, let's go to the orbitals more. Little bit. Okay, this is ENG chapter 20. Huh? This is one more thing I have added. Okay, just for the orbital section. Huh? Okay, so again, right, we talked about this, right? I told you that the energy of the nth level is like this, right? See, In terms of joule, it is minus 2.18 into 10 to power minus 18 joule. Okay.
Okay.
And by z square by n square. And in term of electron volt, this is like this. Got it?
Okay.
And you can see this. See how fast the
Hmm.
electron levels are contracting. Okay. Right? Because right, the energy levels will keep on coming closer very fast, right?
Yeah. Because. Okay.
By n square, right?
Hmm.
N equal to this, ml. This is we know. Now these are the something which we call wave functions. Okay.
Hmm.
Radial wave function and all that. Or maybe we'll just for the timing, I'll just yeah, we'll just stop here. I'll rather have do some problems. Huh? I think it is much more. I think we have done previous year all of these, right?
Yeah. Most of them.
Okay. Okay. Do 70 and 71.
Hmm. Sir, the degeneracy refers to what?
I just told you it is not what you think it is. Degenerate.
Yes, sir.
Degenerate means Google it. Google it. Find
Yes,
it out.
yes, sir. I know what degenerate means, but
Not here.
I know. Yeah, but degenerate.
Calculate. Find out yourself. I already told you twice. Degenerate orbitals means how many orbitals are equal in energy, huh? Right?
Hmm.
Remember now, huh?
Yeah.
Okay.
Yeah. So it's yeah. Sir, I don't know how to do it.
No, 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 no. This is not how I don't know how to do. Okay. What is this response? I don't know how to do. You have to think. In IITs, you won't get the question which you have seen. I mean, you'll get some, but right?
Mm.
Getting the point, right?
Yes, sir.
I've sent.
Sir, I'm not getting it.
Okay. Let's see. So for the hydrogen atom, they are saying that not considering the degeneracy of the second excited state of H atom is 9. No? Second excited state means n equal to 3, right?
Yeah.
N is 3. So in 3, I can have 3s, 3p, and 3d orbitals,
Hmm.
right?
Yes.
So I'll just write this as 3px, 3py, 3pz, 3dxy, 3dyz,
Hmm.
3dzx, 3dx square y square, and 3dz square, right?
Hmm.
So how many total? 9, huh?
9. Yes.
So degeneracy is 9, right? For H atom, right?
Oh,
Okay.
okay.
Now you try. Not then I'll tell. No fun in telling, huh?
Hmm. Not really, sir.
Okay. Now we are talking about H negative, right?
Hmm.
It means how many electrons this has? 2 electrons, right?
Yeah, one extra.
So one is, so we are talking about the third level, right?
Yeah.
So first 2s, this, right? This is
Yeah.
how the levels will be right now.
Yeah.
So this is the first, this is the ground state, this is the first excited state, and this is the second excited state, right?
Okay.
So how many orbitals equal in energy? 3, right?
Hmm.
So degeneracy is,
3. Oh,
got it?
okay. Sir, but then I didn't really get the 2px, 2py thing.
Yeah.
Sir, uh,
You did not, you got everything, you just got your head messed up with the degeneracy thing. And you convinced yourself that you don't know it.
no, sir. Uh,
Yes. There's no here. That is how you convinced yourself. Now you got it?
I mean, mm, not exactly, sir. I told you the 2px 2py thing.
What did you tell me? What do you want to ask?
Sir, I didn't really understand how
Hmm.
2px 2py and 2pz come on top, and then like,
Because we just discussed this, right? We said that in multi-electrons, n plus L value decide the energy levels, right?
yes,
So
uh,
2px, 2py, 2pz will come on the top, right? This is what we discussed here, right? Today, while drawing so many electronic configurations. See?
yes, sir. But uh, uh,
How, what is the deciding factor for multi-electron? N plus L, right?
right,
So what is the N plus L for this? 1. What is the N plus L for this? 2. What is the N plus L for this? All 3. And they're tied. So N will decide and N again is same.
mm,
Right?
uh,
Yeah, keep thinking. Ask whatever you want to ask. For hydrogen, for single electron system, it will only depend on N. So all 2s will have the same energy, right?
yeah. So
2s will be equal to 2px will be equal to 2py equal to 2pz. Okay. Think. Let's see here. Where we are. See. Huh?
mm, okay. Uh, okay, sir. I think I got it.
Take a while. Take a while. I've sent up one file to your father. You have to practice daily 1 hour meditation there.
Okay, sir.
And you have to message me daily on the group if you have done it or not.
Yes, sir. Yes, sir. I think I understood it now.
Yeah, many electrons. This is for hydrogen.
Okay.
right?
Hmm.
Just take a while, take a while, take a while. What is the degeneracy of the first excited state in hydrogen?
One, because there's.
First excited state.
Oh, that's okay. Then that's force. Because
What is the degeneracy of the first excited state here?
so still one because it jumps to 2s, right?
What is the degeneracy of the third,
3,
fourth,
1, I guess.
fifth,
3,
sixth,
1,
seventh,
5,
eighth?
3.
Do 71st.
Sir, is the answer 6?
The total number of yeah, 6. Okay, nice. Do 74.
Okay. So is the answer 16?
16, huh?
Yeah.
I don't think so. Check again.
Mm.
See, it is integer answer type question. So I think only 0 to 9.
Okay. So is the answer 9?
Yeah, I think answer is 9. Nice. Try to do 58. Like one can match more than one, huh? See, read the question here. Quantum numbers.
Yes, sir. A matches to Q, I think. Then D matches to P and Q.
D or
Sir,
B? Bombay.
so D. Delhi.
Okay.
Uh, I'm not sure about B and C.
Think more, think more. And refer, right?
Sir,
Open an alternate window,
okay.
this RC, and then look at what Schrodinger uncle is telling us. Okay? Here,
Okay.
let us name it Schrodinger equation.
Sir, B is all of them. And C is for everything except spin.
B is for all of them, right?
Yeah.
And C?
Everything except spin.
Okay. And D?
Sir, only P and Q.
No, why not R? Because probability density is INLM, right?
Oh, right. Yeah. Oh,
Okay.
okay.
So you got it, huh?
Hmm.
A is
Sir, yeah, only Q.
B,
P, comma Q.
C,
P, Q, and R.
D. Got it?
Yeah.
Okay, we'll come to this when we discuss more about the orbitals. Try this.
Sir, I can open an alternate window and look at the theory.
Yes. Anyways, you can do this and send it to me. I have next class, okay? Yeah?
Okay, sir.
Send it to me, okay? Do it. It's a good question. Huh?
Okay.
Should be able to do it. Okay, Shreyas. Take care.
Okay, sir. Okay.
Bye.